Hello. In this video we're going to calculate the work done using a line integral. So let's say we're given a vector field f and its components are y, I minus x, j, okay, where I is the unit vector in the x direction and j is the unit vector in the y direction. And let's say we have a curve inside this vector field. More precisely, this is the unit circle with radius 1. And in parametric equations, c is our curve, we have x of t equals cosine t and y of t equals sine t. So this is exactly the same as saying x squared plus y squared equals 1, okay? This is the unit circle in the anti-clockwise direction. Okay, and t goes from 0 to 2 pi. You can think of t as being the angle, okay? So basically, the work done is of course your force times your distance. So in this example, we're going to think of a particle moving on this unit circle in the anti-clockwise direction against this vector field that's moving in the opposite direction given by these blue arrows. So we should find that the work done by our vector field f is negative. So how do we start? Well, our curve is x of t equals cosine t and y of t is sine t, and we have dr. So basically, we need to make this a vector-valued function, okay? So, r is a function of x and y, but I'll put it as t in general, okay? So it's simply going to be x, well, x is cosine of t, times I, and then we add y, well, y is sine t. So we get sine of t multiplied by j. Okay, it has the unit circle has no z components. Okay, it's just on the x, y plane. Okay, so that is the vector valued function for our unit sphere. Okay, that is exactly the same as this parametric equation. Okay, r of t. But we have dr. So how do we calculate dr? Well, we know how to calculate the derivative of a vector valued function. So let's calculate the derivative. We have dr by dt. Okay, this is going to equal the derivative of x multiplied by I plus the derivative of y, of the y component of r with respect to t times j. Alright, so therefore, what is the derivative of x? The derivative of x, remember x is cosine t, the derivative of cosine t is minus sine t. So we get minus sine of t times I, and then we add the derivative of y with respect to t. The derivative of sine t is cosine t. So we add the cosine of t times j, okay? This is equal to the derivative of r. But we just want dr, our differential. Therefore, if we times both sides of the equation by t, okay, therefore we get dr. So we multiply this whole expression by dt. Okay? Now, just to remind you, remember the work done is force times distance. dr is just a tiny distance on our unit circle, okay, given by minus sine ti plus cosine t times j. And basically, when taking the dot product, you literally multiply that tiny differential on your circle by the component of the vector field in that direction, okay? In other words, the direction, the component of the vector field are acting on the unit circle, because we don't care about the vectors that have got nothing to do with the unit circle, like this one here. We want the component of the vector field acting on the unit circle, okay? And basically, we add all of the tiny distances multiplied by the tiny components of the force by taking the integral, okay? The line integral of curve C. So just to get that out of the way, okay? Right, so we've calculated our dr, our tiny distance. So we can go ahead and take the dot products. So our line integral, it's our curve C, okay? So t goes from what? Where it says we goes from 0 to 2 pi. Alright, so we can say our limits of integration go from 0 to 2 pi. And we simply take the dot product with our vector field, which was yi minus xj. So we simply take the component, the x component of our dr, and multiply it by the x component of a vector field, which is y. So therefore we get minus y sine t, okay? And then we add to that cosine t multiplied by the y term of our vector field, which is x. So actually, well, it's minus x, so this actually becomes minus x, okay, multiplied by cosine of t, multiplied by dt. Okay, this is just your ordinary integration techniques, okay? So what is y and x? Well, we saw that before. We got x of t equals cosine t, and y of t is sine t. Okay, this looks promising. So therefore, this integral becomes the integral of 0 to 2 pi of minus y. But y is sine t, so this becomes minus sine squared t. Okay, what's x? X is cosine t, so this becomes minus cosine squared t dt. Alright? So we know our, well, hopefully we know this very simple trigonometric identity. It is sine squared t plus cosine squared t equals 1. So therefore we can multiply this integral by minus 1, that becomes a plus, and that becomes a plus. Therefore, this integrand becomes 1. Okay, so what we're left with is an extremely easy integral. It's simply the integral from 0 to 2 pi, okay, the parameter t, of 1 dt. This is equal to, well, if you integrate 1 with respect to t, 1 is a constant, you just get t, okay? And you simply evaluate t from 0 to 2 pi, okay? Okay, so basically, you put 2 pi in for t minus 0 into t. That's 2 pi minus 0, which is 2 pi. But don't forget, we had a negative out here. So therefore, our work done is negative 2 pi. Okay? So our work done is a negative 2 pi. Well, that makes sense what we just said earlier in the start of the video. The work done on a particle moving in the anti-clockwise direction on our unit circle, okay, the work done by the vector field, okay, or the components of the vector field acting on the unit circle, is going to be doing negative work. It's in the complete opposite direction to the movement of a particle. So therefore, the work done by a vector field, f, of yi minus xj on the unit circle is minus 2 pi, your negative work done. I hope that helps, and I'll see you in the next video.